आपला आवाज है आप
The Indian Association of Structural Engineers, also known as IS-Struct-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IS-Struct-E is registered under the Societies Registration Act 21 of 1860. IS-Struct-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IS-Struct-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar as its president. IS-Struct-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IS-Struct-E has collaboration with various international professional like-minded associations and institutions. IS-Struct-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IS-Struct-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IS-Struct-E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs, seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IS-Struct-E's activities are widely appreciated and known for quality technical contents. IS-Struct-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IS-Struct-E's publications are becoming popular with time. IS-Struct-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IS-Struct-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IS-Struct-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IS-Struct-E has its student chapters in several leading engineering institutions as well. Membership of IS-Struct-E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IS-Struct-E is available on its website www.is-struct-e.in. istruct.co.in.
Yeah, Dhawan sir,
Hello.
please start.
Okay. Dear friends, on behalf of Indian Association of Structural Engineers, we welcome you all to participate in the webinar. The topic of today's webinar is performance-based seismic analysis of a mixed-use high-rise building structures in San Francisco. Uh, uh, Brief about the speaker. Engineer Abhinav Bindal graduated and did his BTech in civil engineering from IIT Delhi, and thereafter he went to the most prestigious university in the world and did his master's from Stanford University. Thereafter, he joined as structural engineer in a leading consultant in Los Angeles and worked there as structural engineer for about 5 years. Currently, engineer Abhinav Bindal is a senior computational engineer in NAB Yusuf Associate Structural Engineer, Los Angeles, and has over 8 years of experience in the structural design. He's a young, bright engineer and was topper in civil engineering from IIT. Now, brief about the important topic. As I said, the topic is performance-based seismic analysis of a mixed-use high-rise in San Francisco. His presentation explores performance-based seismic design and analysis of a mixed-use high-rise development in San Francisco, where seismic considerations are paramount. The project involved detailed nonlinear dynamic analysis incorporating site-specific response spectra and seismic hazard assessments tailored to the site's unique conditions. The design aimed to ensure structural resilience through the careful consideration of both structural and non-structural elements. The development features damping systems and moment frames to mitigate focus on optimizing the building's performance under various. His lecture would highlight how performance-based seismic design could be applied to enhance safety and functionality in urban environments. Now, I request Engineer Abhinav Bindal to proceed. Abhinav, please continue.
Hello. Hey, so let me share my screen and let's get started. Let me know if you can see the screen.
Yes, sir.
All right, so today, as mentioned by Dhawan sir, we will be talking about performance-based seismic analysis of mixed-use high-rise. So this building is located in San Francisco, and it's a essential facility, as in it's a bus storage and maintenance facility. And above that, there is a mixed-use residential plus commercial development. So a bit about the building. So the building is supposed to be built in several stages. There are three key components of the building. So there is the bus story, the bus maintenance yard, as I mentioned before, this is called BYC. You will see this acronym later in the presentations. And above that, in the next phase of the project, we will build a joint development, which will be mixed use between housing and commercial portion. And then we will also have this common infrastructure called a BRT tower, which will house vertical circulation elements, utility systems that will be shared between the two portions of the building. So in a essential facility like this, we have to go beyond the code limits and enhance our criteria for performance. So for this structure, we decided to achieve immediate occupancy after design basis earthquake, which was considered as 10% probability of collapse in 50 years. And then collapse prevention level of design for risk targeted maximum considered earthquake. Additionally, we decided to perform nonlinear response history analysis for 11 records, which were selected and scaled per the primary modes of the building. And there was a site-specific response spectrum that was developed for this building. Furthermore, the loss and downtime assessment would be performed on this building to quantify the performance of this building. So a bit about the structural systems. So the BYC, the bus yard, is comprised of movement frames, special reinforced concrete movement frame systems with viscous dampers. We also have long span post-tension beams and slabs in the system. The the housing portion of the structure has BRB steel frames and metal stud walls. Here we are showing two key grid lines of the building. So you can see that there's a movement frame and there are like viscous damping base. And then in the SCC portion, we have the BRB frames. So the structural model of this building was built in ETAPS, and we introduced several nonlinear elements in the building as well. So there are 176 dampers in the building and over 7,000 plastic hinges in the building. So these are the two key plans of the BYC structure. These are the top two floors of the building. And on all the floors except the roof of the building, we have a regular movement frame system with some of the bays as damper bays. And then we have a series of gravity beams in the structure. But on the roof of the BYC, we have this connecting structure to the housing above it. And we also have a green roof here. So there is a lot of landscaping load on this structure at this level. So to facilitate the staged construction approach, we are building these roof beams in two stages. So the first stage, we will have the beam which will serve the BYC portion of the structure, and then we will install couplers over the rebar. And after that, like when the HCC is built, we will build the upper portion of the beam. And this slide shows how the damper bays were modeled. So we went with a realistic modeling of the damper geometry and like how it will be connected to the columns of the structure. And so this creates this special joint region, like where we experience huge demands. So like these are important pieces of the structure. So like special consideration were placed to understand the behavior of these pieces. So regarding the nonlinear hinges, we assigned fiber hinges to the columns and M3 hinges to the beams. For the BRB frames, we introduced some nonlinear axial hinges. Steel beams also got M3 hinges. We plan to add hinges for the columns in the later phases of the project. So currently the project is has just wrapped up the schematic design phase, and we are still under investigation. Like we are still conducting studies on the performance of the building, but I will go on and talk about the performance that we have investigated so far. Um, Before doing that, let me dial back and talk about these nonlinear hinges. So these hinges were defined in ETABS. And to do that, we had to do a design of a building and assign realistic reinforcement to different components of the building. And after that, the properties of the ETABS allows us to define these hinges in the building. And so for the columns, you see we have the fiber hinges, and then for the beams, we have introduced this backbone curve. So after we reach the ultimate capacity, we experience some degradation in the demand, in the capacity of the beams, and we have some residual capacity just for stability of the structure. Similarly, for axial hinges, we have a backbone curve for that too. So this shows the distribution of how many hinges were assigned to different components of the building. One thing to note is that the 88-inch deep beam which we saw at the roof, we did not assign hinges to that because we assumed that those elements will remain linear for the loads we have. So the acceptance criteria for these hinges are taken from ASCE 41. And as I mentioned before, we analyze the structure at both collapse prevention for DBE and, immediate occupancy for DBE and collapse prevention for MCE. And you can see that these checks are very complicated checks that we have to do at each time step. So we did perform that at each time step and then compare it against the demands given by the code. So the seismic weight of the structure is distributed fairly uniformly across the height of the building for different pieces of the structure. And you can see that there is a spike at the roof of the BYC. So this is the roof of the BYC. This is primarily just due to the landscaping loads that are applied at this level. But other than that, the weight per floor area of the structure is fairly uniform. This slide shows the first two primary modes of the building. Pretty well behaved building, but we see that the modes are pretty stiff for this building. So that's what we are dealing with. Now going into results a bit. So since we performed nonlinear response history analysis for the structure, we did this for all the 11 records scaled at DBE as well as the MCE intensity level. After we did the response history analysis, we took the peaks of each ground motion and then averaged it across the 11 motions. So just to give you a scale of how long this iteration was taking. So each run of our model with this full suite of ground motions, and we trimmed the ground motions to maximize our runs. So it was taking around 3 days per run of the model. And since this was a schematic design phase, we had several design options that we were considering. So there was a scheme where only the BYC portion of the structure would be built, when we would have the BYC plus the HCC over it, BYC plus HCC plus the common infrastructure, and so on and so forth. Plus, we also had a lot of iterations and back and forth with the architecture where they gave us an initial design of the components we looked at it, we found out that yes, we need to upsize this column, or we need to move this grid line here to achieve a better performance. So we did all that iterations. And to do that, like, we had to create a lot of tools to be able to process the information very fast from a run model. So we did a lot of development of processes to make our process very efficient. So currently I'm presenting the results for the case where we built the full structure. So BYC, and above that HCC, and then next to it, the common infrastructure. So as we can see, like, for the full development, for BYC, we achieved less than 1% drift in both the grid lines, primary grid lines of the structure. And like, all these lines represent different key points in the building across the perimeter of the building. So, so as to bound the behavior of the building. We do see some exceedances above the BYC roof, so in the housing portion of the structure. So this is, we will investigate a bit more about this in the later phases of the project to ensure that the behavior is controlled and that in those grid lines. So similarly, for floor accelerations, we saw very nice behavior for all the grid lines, and we were approximately near the PGA for the site for the BYC. And these two parameters are very important because a lot of non-structural components, the behavior of those are governed by how the floor, like, what is the floor acceleration, and like, what is the interstory drift between different floors. So it's important to know these two parameters. So these two are some of the key parameters that we used. Similarly, for MCE, we can see that all the responses are less than 2% for the BYC. And in this case, even for HCC, it is less than 2%. And then the floor acceleration behavior, is nothing too crazy going on here. So now, like, this is the deformed shape of the structure under amplification factor of 3 for one of the MCE ground motions. And you can see that, like, it's behaving in like the first mode, and it's no surprises there, which is the good news. Now, let's see if I can play this video. Oh yeah, it's playing. So this is the full ground motion, like one of the ground motions, and the behavior of the entire structure under it. And we did several runs to achieve, to get to this state where we were not seeing anything flying off. So this is also one of the things, like, when you start with any model, nothing goes well in the first round, and then you have to do multiple iterations. You have to find out where the issue is in the modeling and like how you're modeling it, and finally you are able to get a model which runs in a sufficient, like in a decent amount of time, and also gives you reasonable results. So it's a very iterative process to get here. So for visual purposes, like, I'm showing an amplification factor of 5 here, and then you can see, so BYC is behaving very nicely. The HCC, there is some like desires for more improvement there. So we are in the process of thinking of revising some of the designs or like the structural framing schemes above, so that we can remove some of the spikes in the drifts that we saw earlier. So the floor, the story shear for each floor here is listed, and you can see that, like, as we go up into the HCC, the story forces are low, and then, like, in the structure below, they increase as we go down. And there's a huge jump here because, again, there is a green there is landscaping here, which increases the story shear. And then we also deaggregated this demand to different components. So they were like gravity columns, which are behaving as they should. They're not taking too much load. A lot of load goes into the special movement frame columns and the viscous damper frame columns. And then the dampers are also doing some heavy lifting here, taking a lot of force themselves. So now going more into what we look for in a performance-based structural analysis. So there are two things here. So first of all, since this was deemed as an essential facility, we had to amplify the demands under BBE. And then there was another amplification added on top of it, which was to account for the immediate occupancy performance objective. So that's why we ended up with a factor of 1.5 for over the mean demands obtained from nonlinear responsive analysis. Similarly, for MCE, since we had a collapse prevention, so that did not add any factor, but we still had to amplify it to account for the fact that this is an essential facility. And we can see that most of the beams in the structure are below the shear stress ratio of 10. And there are a few beams too, in our case, where we exceed the limit of 10 square root F prime C. And this will be addressed in the later stages of the project, where this beam, we would identify how the loads are flowing at that level, and then if needed, we will upsize that beam to reduce the shear stress ratio. Similarly, for the columns, only a few columns, 3 to be exact, exceeded the limits put by us, and for 10 square root F times C. And this will again be addressed in the later phase of the design. So as I said, there are all these damper bays have two portions of the column. So there is this joint region, and then there is the rest of the column. So joint region is a very special piece, and it collects all the load that is coming from the dampers. And then we do see very high demands, shear stress ratios in those joints. So these joint regions would be heavily reinforced, and we would consider how to reinforce them to prevent damage to these areas. So per code, we can go up to 15 square root F prime C for these regions. And we did look at all the locations, and we found out there were a few locations a bit more than what we would like, where we were exceeding that capacity under MCE. For DBE, we were still all good for all these damper regions. So these columns, as we have identified here, would be a main focus of our design and in the next phase of the project. So since we modeled all these plastic hinges in the structure, and the acceptance criteria according to ASC 41 for immediate occupancy is solely based on a deformation-based approach, we had to look at the hinge rotations and how we are performing for those. And these are the real acceptance criteria for us. And you can see that this right now I'm showing for immediate occupancy, which is a very stringent criteria to meet. And we are doing very well on all the beams. We are not exceeding even the degradation initiation limit as put by the code. And we are very far from the sorry. So the hinge initiation degrades much later than what the code requires us to do. So the code, like for the immediate occupancy, has a very stringent criteria, which is way below this the degradation limit, and we are below that. So we are doing pretty good with a maximum DCR of 0.92 for like considering all the locations. And as we looked before, this hinge rotation is the capacity is a function of shear stress ratio. So for each beam, we looked at what is the stress ratio at that location to compare the demand obtained with the location specific capacity to get this DCR that we are looking at here. And similarly for columns, we have to look more into this, but there are 16 locations where we were exceeding the hinge rotation capacity under DBE. And all these were concentrated on one of the grid lines. So we need to rebalance the dampers on that grid line so that like the loads are not all are distributed well in the rest of the structure. For MCE, we are doing pretty well. The performance objective set by the code for collapse prevention is much higher than when the hinge degradation initiates for beams. So we are again well below the limits, and we are doing pretty good for beams. Even for the columns, there are no columns exceeding the acceptance criteria under MCE. So it's a pretty good response. There is one more thing that I didn't mention here. So you can see that here I'm looking at average axial force in the columns to calculate the capacity of the hinges. And I'm also looking at mean rotation demands. So I also checked the maximum of both. So like maximum compression force and maximum rotation demands. And we were good for that too. So that I have not mentioned here, but like that is something we did too. And finally, for the BRB hinges, we have checked the strains in the elements, and we are all below 3 times the yield capacity, which is acceptable. So this brings us to the end of our presentation, and now we can entertain any questions you might have. Dhawan sir, you are muted if you are saying anything.
धवन सर आप म्यूटेड हैं।
My voice is audible?
Yes.
Before I request Vikas to, there are a few questions which we'll be asking you. Before that, my small queries to you. The first one is, what is the role of a structural engineer during construction stage? That is my first question.
So yes, so during construction stage, like in US, we are required to do regular site visits to the site. We ensure that like things are being constructed the way we intended them to be constructed. So apart from that, like, so these are the part of our regular site visits. Apart from that, like there is a inspector assigned to oversee all the construction here. And like, so this is a third party inspection that happens, and they are more, well, like they're on the site all the time, so they obviously see more than what we do. So they bring up issues that they see per their interpretation of the drawing to us, and we answer them as well when we are doing the site visits. Other than that, like daily we get like a lot of RFIs and questions from the site, from the construction team, where they are asking us for interpretation or any clarification that might be needed. and it's our role to answer them as soon as possible so that the construction can proceed as expected.
My second question, just how much energy would be taken by this viscous damper out of total energy? How much energy would be taken by, in your example that you are given?
I did not include that slide here, so the numbers are not fresh in my mind. So I think it was around 15 to 20% of the total energy was dissipated by the viscous dampers.
And then final, this you talked about DBE and MCE.
Yes.
Here, design basis earthquake and then maximum concentration of earthquake. What is the ratio that normally you take in your design?
So normally it is 2/3 per the code, but that is not what we use. So our objectives was more governed by the return period. So we had a 475 days return period for DBE, and MCE, I'm forgetting, but around 2,400 days for MCE. And so we scaled our ground motions to target that return period.
Mm-hmm. Vikas, please now the other questions that our participants have asked, just one by one.
Yeah, so there are few questions. First question is asked by Saeed Anwar Ali. Which software is used for this performance-based design analysis using BRBs and seismic dampers?
So we used the ETABS Ultimate license for this design and analysis. And the Ultimate license allows us to introduce nonlinear hinges, the backbone curves inside the structure. So we use that.
Okay, sir. Sir, another question from him is, what should we consider response reduction for a structure?
So since this is not a linear analysis and we do a nonlinear response history analysis, we only introduce some factors to the elements to incorporate cracking. And beyond that, we don't add any more factors over the results that we get from the analysis.
Okay, sir. Sir, another question is from Dr. Satish Sharma. Kindly elaborate viscous damping system used in the work.
Right. So as of now, since we are very early in this project, we do not have a specific damper in mind, but we did use like a nonlinear viscous damper, which has exponential it's a viscous damper that is activated by the differential movement of the floors with the differential velocities, and we have like an exponent over the velocity differential. And these are currently just to get some damping forces, which we will use to select the actual damper in the future.
Mr. Venkata Gavaraju asked, is the hinge data based on testing concrete and steel materials or only code? But I think the backbone curve is based on test data.
That is true. So there have been a lot of tests that have been done in the past to fit a backbone curve to the behavior of these components. So these are there's some guidance on how to get that in the code. So we use that data to get our backbone curves. We did not do some testing ourselves to get those backbone curves.
Okay, sir. Mr. Biswaram Gosai asked, what is the energy dissipation of the damper and what is the capacity of the damper used in this project?
So energy dissipation, we've already answered. So it was around like 50 to 20% of the energy was dissipated in the dampers. So right now the capacity is still being, we are still looking at that because we are looking at the demands in these damper elements, and we will select a damper based on that in the future.
Okay, sir. Mr. Rama Salman asked, is the slab and infill walls contribution considered as a part of the resistance system?
So slab, yes. Infill walls, no. So there are walls in the HCC portion of the structure that were modeled, but we did not consider any lateral contribution due to those walls. So the primary force resistant systems are BRB frames in the housing portion of the structure, and the movement frames with some damper bays in the BYC portion of the structure.
Okay, sir. Anushka Jindal asks, very interesting project. Can you tell some challenges you faced during this project?
So there were several challenges actually. So since this was a very early phase of a project, and actually we were required to go way beyond what would be expected for us at a SD level project. So this is the work I've presented so far is actually the stuff you would do when you were in design development phase of a project. So we had to ramp up our post-processing and like our analysis much faster. And then it was also SD, so the design was changing very quickly. So we had to have a very quick turnaround of our interpretation of results and provide suggestions to the architects as to how or what they should modify if they would. But like we were playing a catch-up game, and like I mentioned before that like this model took 3 days to run. So we had that time where we were like just building models, setting it to run, and there were like several design schemes in at one time. So we had to run all of them in parallel. And after that, there was a lot of processing, like interpretation of results. So I would say the time crunch was the main challenge here. And
Yes, Mr. Harsh Khatri asked, how much energy dissipated by FRP and performance of FRP? How much energy dissipated by FRP and performance of FRP?
FRP, I'm not sure what you mean by that. As I mentioned, like I do not have those numbers in front of me, and I don't remember that on the top of my head.
Okay. Yes, sir. So, Mr. Pranat Pal Srivastava, how the slabs and columns behave during the analysis?
So the analysis was actually mostly governed by the hinges. So since each column and each beam was given a hinge, we were expecting that all the damages would be concentrated in those elements. And the expectation was that as a hinge reaches the ultimate capacity, the performance of that would degrade and the load would be redistributed to the surrounding hinges. So that's how the intention was behind the modeling. The slabs, we modeled them mostly as linear elements. So they are there just for distributing the loads and introducing the loads in the framing system, but like they are not undergoing nonlinear behavior.
Sir, Mr. BP Karamchandani asked, how much time took to model the joint structure with dampers?
So I would say I got into this project in the middle of the project. So the initial modeling of the was already done, but like we had to modify the model every time we got a new scheme. So all those modifications we were trying to get it done in like a day or so. and so that we can set it to run, and by the end of the week we would have the results that we would send back to the architects.
Okay, sir. Mr. Pranatpal again. Do some of them have developed full capacity plastic hinges?
No. This is good also because we were able to we sized the columns and we provided realistic reinforcement in them. So if they were developing any hinges, we caught them early on, and we designed the columns so that none of the hinges were actually forming during the analysis.
Okay, sir. Mr. Vishwaram Gosain, it seems that you have used horizontal damper connecting joint to joint. What measure is taken to strengthen joints?
So this is a good question, and this is something that is part of our next phase, where we would provide details on how this joint could be constructed. But like, just to give a very high level overview of this, we would have like plates covering this joint region to really hold that in place, and we would have rods going through that to increase the compression in those joints. But like, we will be going into a lot more details, developing those details for how the joints would be detailed and constructed.
Okay, sir. Yes. Mr. Ramakrishnan Sangani asked, is the backbone curve from ASC 41-17 is ETABS or perform 3D, which is good for NLRHA?
So this is from AC 14-17 and AC 41-17, and we did not use perform for this analysis. We did everything in ETABS, and ETABS in the latest version can we can introduce backbone curves there, and we can do everything the perform can, but in ETABS. Perform has this issue with a lot of like the data not being in a user friendly format. So we're glad that ETABS can now handle all of that. So that's the software we use inside the firm.
Okay. So Mr. Alisam Sakamon maybe asked, can you use European, American, and Canadian standards for your models? Means are you using?
We are using American standards because this is in America, but I've seen like in other countries, there's usually it's acceptable to use codes of other countries as long as the panel agrees. So a project like this has an expert panel that is assigned to a project, and all these conversations are like early conversations you have with the panel that like, yes, I'm using this code, that code, and then if the expert panel also agrees with your assessment and selection, you go ahead. If they don't agree and they say like use this code or like add this criteria in your design, we modify the design based on that discussion we have with the expert panel.
Okay, so Mr. Ayan Srivastava asked, is the usage of stiffness modifier as per codes to stimulate cracked sections properties required during non-linear modeling of structural components?
Here it was, and we did use them.
Sir, Mr. Ramakrishnan again, have you modeled the slab as non-linear strips as per TBI and LAT BSDC or without slab? For NL with the slab, the model generally take time, right?
It does take time. So we have modeled linear slabs, like the slabs are behaving linearly right now. In the future, we may explore like a test model with like a non-linear slab as well. But right now we have not used that.
Okay, so Mr. Bijoy Varghese asked, very interesting. Was there any problem with service design like plumbing, electric ducts, etc. during structural design. Can you share such experience? How could you solve it?
Can you repeat the question?
Was there any problem with service design, plumbing, electrical ducts, etc. during structural design? Can you share such experience? How could you solve it?
Okay. So in this project, we have not gone to that level of design, but in the past, I've worked on some projects where those we did look at all of that. So it was like a base isolated structure, and we had to look at how these components would behave at the interface at the isolation level. So there's a lot of consideration that goes into how the joints will react, how different pieces will react, and we do look at that in the field and try to ensure that there are no surprises later on.
Yes, sir. Mr. Ashish Patel, is there any particular reason for choosing viscous damper? Any alternative damper that can be more economical and beneficial according to you?
Viscous dampers is pretty economical. We have like that's pretty standard in the industry that we have used here. I have also seen like recently there have been some kinetic dampers that have been used in the structures. So they mostly just rely on viscoelastic response of the material, and it's performing quite well. So we have been looking at some of those as well, and who knows, maybe we end up using those in this building. We haven't selected the dampers yet, so that may be a consideration as well. But the benefit for those is that, like, for viscous dampers, you have a monitoring program, and they have to be exposed for someone to go and look at every at a certain interval and after every major earthquake event. But for these viscoelastic dampers, you can just hide them inside your like beams, for example, and that's pretty enticing to all the architects out there. So we have started to look at that in some of our other projects, and who knows, maybe we end up using those here as well.
Okay, sir. Mr. Harsh Khatri again. Do you use any specified design for FRP?
I don't know if I don't think we have FRPs here.
Okay, sir. Mr. Pranat Pal again. Can we integrate this model with base isolators? If yes, then what would be the probable analysis results?
Can you repeat this question again?
Can we integrate this model with base isolators? If yes, then what would be the probable analysis results?
Well, base isolator is a very different kind of base isolation is a very different kind of project, and it is actually very costly to do. So we same building cannot directly be transferred to a base isolation system. Normally, what we do is that we expect the structure to behave linearly when we have a base isolation system. So the design would probably look very different from what it is right now. I cannot comment on how it will behave, but usually the economics of using such a system outweighs the benefits provided by that for this application of the structure that we are seeing. I've used base isolation in like a museum project before where it made sense to use that, but not here.
Okay, so this is the last question by Mr. Syed Anwar Ali. Is there any possibility to introduce PT slab and beam?
There is post-tensioning slab and beams in this project already.
Okay, so yes, the one more question has come, sir. Is it necessary to use damper and bracing at same location as it reflects in your model?
So the braces are provided just for stability of the damping systems. That again goes into the more of like a drawing question, like how will we actually configure these dampers? That is still on the drawing board as to how we will end up doing that. But as of now, this is how we are approximating we will be doing it.
Okay, sir. So Dr. Atul K. Desai have considered vertical earthquakes component in seismic analysis.
Yes, I forgot to mention that. All the we have provided three directional earthquakes here. So there is earthquake in X, Y, and Z direction.
Yes, sir. There are two more questions. Is there any relaxation in stiffness modifiers provided by IS 1893?
We don't use IS 1893 for this building. We used actually the PRTPI recommendations for the stiffness modifier.
Okay, sir. Mr. Ashik, can we break a complex structure into a simple one and design it as individually structure? Can we consider expansion joint, and how do you define dampers in ETABS? There are two questions from Mr. Ashik.
First one is pretty general, so I would refrain from answering that. Like that is a choice of a designer. How would they actually go about doing analysis of any project? The damper design, again, like it is something that changes very often in ETABS. So I would recommend just looking at the analysis guide and finding out how you define this in ETABS.
Okay, so this is the last one. Can we optimize structural cost by using dampers?
Yes, and that is the point of using dampers. So without dampers, we were seeing here that, sorry, there was, okay. So we were seeing that without the dampers, there were significantly higher loads that were being taken by the structural components. So we would have to upsize them significantly to be able to achieve same structural performance that we are right now. So introduction of dampers is definitely a conversation as to like, is it helping your structure or not? So you need to look at you need to design the structure properly after introducing the dampers and carefully look at the economics of like, does it make sense to use? And in our project, it did. So that's why we kept it.
Yeah, so this is the last one. Sorry. Is that, Mr. Regan Mohan asked, is that any specific code provision for erection of damper system?
Not that I know of.
Okay, sir. Thank you, sir. Dhawan, sir, please.
Friends, now let me conclude. Friends, Engineer Abhinay Bindal has given an excellent presentation in the webinar. The topic has been very, very useful. That is the performance-based seismic analysis of a mixed use high-rise the building structure. And then where he explained us the involved detailed nonlinear dynamic analysis incorporating site-specific response spectra and seismic hazard assessment tailored to the site's unique conditions. I'm sure over 200 participants must have gained something. And now, as per our usual program, the next monthly lecture we'll have on 26th of September. That too by a different speaker on a different topic. So thank you, Abhinay, for sparing time and then getting up early morning to share your knowledge and experience to us. We are really grateful to you. Thank you. Thank you so much.
Thank you for having me here.
Okay.